Hey, what's up, guys? This is Chung here. So today, let's take a look at the last problem of this week's weekly contest, which is 1617. Count subtrees with max distance between cities. Mm, I think this is a great problem. It's a good hard problem here. So it's a tree or graph problem basically. Basically there we have n cities numbered from 1 to n. And then we have edges between those cities, right? And then and so then it says there exists a unique path between each pair of cities. In other words, the cities form a tree. Okay, because so which means that it's not a graph, it's a tree, right? So tree is there's no circle in the tree. So which means that you know uh, that's why it says there's only one unique path between two nodes here. If we have a if it's a graph, it means that we may have like a circle, right? For example, this one. With a circle, between two nodes, there are like more than one. Basically the path is not unique. So this is like a graph. But in our case, it's a tree. Okay, cool. So that's a prerequisite. And a subtree, right? So a subtree is like it's any subtree, right? Basically, the subtree is a subset of cities where each node is connected. That's the definition of a subtree. Okay, so that's the second one. And what this problem is asking us to do is basically it asks us to find uh, for each of the distance here, right? So for the distance, the distance in the maximum distance, in the subtree, right, is in the range of 1 to n minus 1 because we only have like up to n nodes, right? So that's why the maximum distance is n minus 1. So the distance between like in the subtree is this, right? So let's say we have this subtree here, and the maximum distance is 1. And if we have this subtree, so the max distance is 2 in this case because it says the max between any two cities in the subtree is equal to D here. Okay. And same thing for this one. If this is another subtree, so the maximum distance in this subtree is also 2. Okay. So now it tells you how to define the maximum distance in the subtree. And in the end, it asks you to return like a list of size n minus 1 where at the index I here, it 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 asks you to calculate how many subtrees can have this max distance. So for example, right, we have n4 nodes here, and that's why in the end we need to return like n minus 1 elements here, because with n nodes the maximum distance we can form is 3, right? Is 3. That's going to be a linear, right? So that's the maximum possible distance for a tree with 4 nodes. That's a 3, 1, 2, and 3. So that's why it asks you to return like a n minus 1 size of a list, and at the first one represents how many subtrees have the maximum distance equal to 1. And the second one is the how many subtrees has the maximum distance of 2. Same thing for this. Okay, that's why, you know, with the given edges here, right? That's the visualization of the tree here. So uh, we have a subtree 1, 2, 2, 3, and 2, 4, whose maximum distance is 1, and we have 1, 2, 3, and 1, 2, 4, right? Has the max distance equals to 2, and where in terms of 3, there's no such subtree. And for the others, like 1, 3, 4, 1, 3, 4, those nodes, they cannot form a subtree because they are not connected to each other. Okay, cool. So that's basically the description of the problem, you know. Yeah. So, mm, I think the first step is if we just follow the if we just follow the mm, this problem, you know, the first thing first is how can we find all the subtrees, right, inside a tree here. I mean, because I was like, I was trying to use like a DFS search, you know, basically, okay, I just start from one here, and then with its edge, because I'm going to create a graph, right? Build a graph based on the edges here. So with this one here, can I go to two, and from two I need to go to three and four? Maybe I can use some backtracking mechanism to do that, but it didn't work quite well for me because, you know, from one to two, right? So from one to two, we can have one, two, one, two, three, and one, two, four. But then I need to move to two, right? So when I move to two here, uh, I I need to somehow exclude two and one because one, two, and two and one they are the same, but two, three, and two, four they are not. So I kind of struggled there. So and it didn't basically didn't work out. Didn't work out quite well for me. You know, I mean, if you guys know how to get out subtrees by using a simple like DFS traverse, yeah, please do let me know. So basically, another if that approach didn't work, you know, another way of getting all the subtrees, you know, if you notice that, you know, the node is only within 15, so which means that we can just brute force, right? Trying all the combinations to the nodes. Basically, no, this one is like combinations, right? So the combinations of all the combinations of the nodes here, and we for each of the combinations, we check if those nodes, that combination can form a subtree. Right, so to form a tree, it simply we just simply need to check if those nodes can be connected together. So, okay, so that's the first step. I mean, so now we just need to loop through all the combinations, right? So to loop through all the combinations, now it's again we need to use a bit mask, right? Again, so it's like gonna be from zero to what to I uh sorry not I. So this is one do a bit shift to the left by n, right? So that's the range of all the combinations. Basically, it's a range of the 2 to the power of n, okay? Because for each of the nodes, we have two options. We either pick it or we don't pick it, okay? And that's the total. So the total combination is 2 to the power of n. And within those combinations, right? We just need to have like a helper functions to help us find to check two things. First is if that if this combination or if in term now we have a mask here, right? So if this mask can form a subtree, okay, and if it can, and then what's the maximum distance for that subtree? So that's the second problem we need to solve here, right? And in terms of the maximum distance of a subtree, and to calculate that, let's assuming we have a we have this 2, 3, and 4. So the maximum distance for this subtree is 2. Okay, but how can we calculate that? At least for me, the way I'm using is the basically I just try to use each node as a root node, or as a root node or as a starting point. And then I'm using like a BFI search to search all the rest nodes starting from there. And among all those searches, I will choose the maximum distance based on that starting point. So which means that for this subtree, I'm going to do a search 3 times. Okay. So the first time is I'm going to start from 2 here, right? So from 2, I do a BFI search. So if I start from 2, the distance, right, I will get is 1, because from 2 I can get both 3 and 4 by using a BFI search. Okay, that's 1. But 1 is not the answer we're looking for here. We're looking for the maximum distance. So now the next one, next I will be searching from 3 here. So if I search from 3, the BFI search, the first time I'm to get 1, the second time I'm going to get a 2 here. So if I start if I start searching from node 3 here, I'll get 2 here. Same thing for 4 here. So basically I just do search a BFI search 3 times, starting from each of the nodes, and I will get the biggest number among them. Okay, so that's the way to calculate the maximum distance. Um, there might be some other ways of doing it, but I just haven't really thought about that. If you guys have any other ways of getting the maximum distance given like a subtree, and I would definitely love to know that. Okay, cool. So with that, so I think okay, once we have the maximum distance, right, out of for our subtree, we can simply save that into our final answer. So our final answer is going to be like a bucket, right? Like a bucket with a bunch of zeros. Since this one is zero based, let's say we have a distance, right? We have a distance equals to 2 here. So which means that uh, uh, since this one is a zero based and we have to do a 2 minus 1, basically we simply increase the total count for this one by 1. So because now this one will become to 1, because that's the distance, that's the count for the for the subtree who has the maximum distance equals to 2 here, right? Cool. I think that's it. Let me try to start coding here, and I will explain a little bit more here. And cool. So first thing first, I need to create a graph, right? So that we can use this graph to connect those combinations. Okay, so the graph is like a list, default dictionary list, and for u and v in edges. Okay, and we have a graph u append v and graph v dot append u. Okay, so now so here I'm going to have an answer here, right? Like I said, the answer is the size of n minus 1. Okay, and then here I'm going to have my mask here, right? So the mask is in the range of the one basically 2 to the power of n. Okay, so mm, yeah, and I'm gonna have like a d here, right? So the distance I'm getting here is that like I'm going to have a helper functions called get max distance, right? So I'm going to pass in this mask here. So where this mask can tell us which nodes it contains, right? And here in the end, I simply return the answer. So basically, that's the structure of this problem. Um, we just we just try all the combinations here. So now it's we need to implement this get max distance, right? We have a mask here. Okay. Yeah. So this get mask the get max distance helper functions will do 2 things. First, it will check if the nodes within this mask can form like a tree. If it can, I mean, we'll return the maximum distance of of that. So basically, I will do two things at the same time. And so we're gonna have like an answer equal to 0, right? That's gonna be our final answers. And then, so I think you guys probably have already know that to find the which node we have is set to 1, which bit is set to 1 from this mask, we simply do a I in range, right? So in n, basically that's the total number of bits in this mask here. And to check which if this bit has a 1, we simply do an AND of a 1 uh, uh, left shift by I. Okay, so this one means that, okay, so now this mask has the or this bit map this bit has this has value set to 1. and and then we simply need to start to do a BFS search from here. Okay, we try to link all the other nodes within this mask. Okay, uh, I think one thing that we need to be careful here is that, as you guys can see here, we're doing like when we're doing like this bit manipulations here, the node we're using here is 0 based. Okay, but here, right? So, but here the node is 1 based. So which means that when we build the graph here, we need to convert them to 0 based so that they can be aligned with the node in the bit mask here. Okay. So now we have that, and yeah, and like I said, since we're going to try to do a BFS search for each of the node in this mask here, that's why we need to I'm going to have like a temp mask here, because I'm going to use this mask to I mean to keep track of the if this node has been connected or not. Okay, so which means I'm going to use a temp mask here. Okay, for this. Cool. So now, and we have chosen this node here, so which means that we have basically, this node has been visited. Okay, we can either use like a visited like set, or we can simply use this mask to help us mark if this node has been visited or not. Okay, so now this node has been visited, we simply can mark this node in the mask. So we mark this one by doing like XOR, right? With this one, with this bit mask here. So we have visited these nodes. Now we just need to, or we just mark that value in that for this bit in the mask from 1 to 0. That's how we do a mark it. Okay. Now we have a D equals to 0. Now the rest is just the regular BFS search template. Okay, we do a while Q here for this in range length of the queue, right? So, and we have a node equals to q dot pop left, okay? And then we have a neighbor, right? So for neighbor in the graph of the of the node here, right? So, and here we need to check if the neighbor has been has been visited or not. Okay, right. So since I'm using this mask here to note to store if this node has been visited, we can simply do this. If the temp mask do an end, right, with this one, so we can simply check if this neighbor has the bit value 1 in this mask. If it has, then it means that it has not been visited before. Okay, then we can simply do a q dot append neighbor, right? So now we need to mark it again. So I can just copy the same thing here, right? So now we're marking this neighbor to be visited here. Okay, so then if the while loop is finished, no, if the for loop is finished, we simply do a d plus 1. That's the basically this one can help us uh, track the current distance. Okay, so like I said, we will be checking two things. First is the distance. Second one is that if we also need to check if the current mask can form like a tree. So if we are using the like a visited set here, right? Uh, uh, we can simply check if this visited set, the length of this one is the same of the of the total ones we have in this mask. That's one way of doing it, and a a, a tricky way or a quick way of doing this is that once we have a for loop here, as you guys can see, we are marking all the nodes from 1 to 0. So what does this mean? It means that if all the nodes can form like a tree by the end of this while loop, right? So all the bits value in the temp mask should be equal to 0. Then, right? So here we can simply check if the temp mask is equal is not to 0, basically, right? So if there still has some there's still some node that has not been visited, then it means that this mask, the nodes for this mask cannot form a subtree. Hence, we can simply return 0 here because we'll be using a 0 here. But yeah, so basically, if d is not 0, and then we do a answer dot d minus 1 plus 1, right? So the minus 1 is like the 0 base stuff, right? So that's how we check the validity of forming a subtree. So if it's valid, then we simply do an answer equals to answer dot sorry max answer dot d, right? Like I said, so remember, so we're using each node as a starting point to do a BFS search so that we can get the maximum distance for this subtree. Okay. Okay, and here, I think we're right here. So here we can simply return the answer. But remember, the answer we're returning here, it should be answer minus 1. Hmm, is answer minus 1? Yeah, I think so. Yeah, let me check. Yeah, it's because if we have two nodes here, so the D will be is 2 in this case. Okay, because for the first time we plus 1, and the second time we also do a plus 1. So that's why in the end we need to return the answer minus 1 here. Okay, so yeah, I think that's that. And but there is like the issue here. Basically, I think we can do a quick check here. Basically, if there's only one node in the mask here, we can simply return 0 because mm, if it's only one node in these things here, we'll do this. Mm, let's try to run the code first. 20 in range. Oh, here. Hmm. Okay, anyway, I'm going to add these things here. Basically, if there's only one bit in the mask has a value 1 there, then we certainly can simply return 0 here because with one node there's no point of forming a subtree, right? So the subtree has at least 2 nodes. Okay, and from a cities subtree, yeah. So how can we? But and then here I'm going to tell you guys a trick here. So given like a binary values, how can we check? How can we check if there's only one bit value in this one here? I mean, of course, you can convert these things to a binary strings, and then you do a count of 1, something like this. Yeah, something like a bin of mask, right? And then you do this 2 here, and then you do a count 1. You do a count 1. That'll definitely give you the answer, right? But there's a quicker way of doing this. So the way we are doing this is that so let's assuming this this bit has 1 here. How can we check that? Think of in this way. Basically, let's mask and mask -1. So what's this one will give you? So what the mask -1 will give you? What it gives you is that, in case, let's say if there's only 1 in this mask here, so the mask -1 will have like a 0, 0, 0, 1, 1, 1, 1. That's the mask -1, which means that this is the most significant place of the previous mask. If you do a -1 there, I mean basically it will revert everything after this to this. And if you do a AND here, if there's only one in this uh, in this in this mask here, so the final answer will equal to 0. If there's another one here, so the final answer will not be equal to 0. Yeah, that's a trick to check if there's only one bit that has 1 as a value. So which means that basically, if this thing is equal to 0, and then we simply can return 0. Yeah. So okay, so let me try to run the code one more time here. Cool. Yeah, I think this 5 that's the issue here. And yeah, so submit. Cool. Yeah, so it's accepted. All right. And how about time and space complexity, right? So let's see. So here we have a for loop, like I said, so that we have a 2 to the power of n here. And inside of get maximum distance, let's see how long will this thing take. So we have n here, right? So for each of we'll have we have n here, right? So we try all the nodes here, which is n, and then for each of the node, we do a BFS search. Okay, so for the BFS search, it can take up to n time as well. Yeah, right. So I think the total complexity is 2 to the power of n times n square. Yep. So that's the time complexity for this. And the space complexity is that just this graph here, right? So I think it's O of the length of the it's O of n. N is the number of the it's total number of edges, right? So total number of edges in a tree is the is n times, yeah, it's n minus 1, I think. We have a, yeah, yeah, something like this. So close to O of n here. So that's the space complexity for this problem. Uh, let me think. Yeah, so I think that's the whole logic for this problem. You know, just to recap real quick here. So here we have this, right? Basically here we uh, try all nodes combinations, right? So we try all the nodes combinations, and here we check the traverse, right? Traverse the nodes from each node as a starting point. Okay, and here if there is still nodes that has not been visited, right? Then not a valid subtree. Okay, right? So now other than that, we just keep tracking of the maximum distance by traversing each node as a starting point. Then we get that. So here check if there is only one node in the mask. Okay, cool. I think that's it for this problem. Let me know what you guys think. I probably didn't do a good job explaining this problem, but I I tried my best. Yeah. Okay. Thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.